Hello, everyone. Very warm welcome from my side. I'm Daniela Mitterberger. I'm co-lead of the Immersive Design Lab at Design++, and from the organizational team of this seminar series, of the autumn seminar series. We want to welcome you to our first lecture of this autumn. We are very, very happy to have a great speaker today here, Corentin Fivet from EPFL Lausanne. If you missed some of our previous lectures, we have a YouTube channel where we post all of our lectures. We also post other talks that we have. So please visit and follow our YouTube channel. Of course, I'm not working alone. I'm here on behalf of the rest of the team of Vera Balmer, which is sitting here, Dr. Daniel Grego, and Michael Kraus, who is also sitting here in the audience. And now I'm very happy to introduce Corentin Fivet. He's Associate Professor of Architecture and Structural Design at EPFL Switzerland, heading the Structural Xploration Lab. The lab research mainly focuses on developing computational design methods to ease the reuse of load-bearing elements in buildings. Before joining the EPFL, Corentin Fivet worked as a researcher and teacher for 2 years at the MIT in the US, and he holds a PhD in engineering and science from UCL Louvain, Belgium. He's author of numerous scientific publications, is regularly invited to give keynotes in Switzerland and abroad, and has won several awards for his work. I'm very excited to hear your talk today about urban mining and reusing for new buildings, transformations, and how we can use circular strategies for environmental benefits to reduce global warming potentials, waste, and material extractions. I'm very excited to hear you talk, and we welcome you.
Thank you, Daniela, for the introduction. Thank you for the invitation. It's always nice to come to Zurich, the sister university, and see familiar faces, of course, as well as new faces. So, yes, okay. I mean, it has become a habit for this type of talks to start with some slides showing the environmental impact of the construction industry in terms of greenhouse gas emissions, waste, and so on. I will spare you that, and I will try not to do that, but still I believe I have to show you this graph because it's actually a combination of two graphs that we are not used to see together. And what do we see here? So we have this curve here showing the amount of CO2 emissions worldwide since the 1970s. At some point, scientists, so in particular people from the IPCC, where this data come from, realized that CO2 is not the only greenhouse gas emission, but there are other greenhouse gas emissions. They started to measure that, and here is the new curve that they have. And in the latest IPCC report from last year, they are showing the amount of effort that will be needed in order to limit global warming to 1.5 degrees. And there are scientists, but there are also humans, and they realize that, you realized before, everyone probably, that this is a target that won't be achieved. So they showed us these other paths that could be followed in order to limit global warming now to 2 degrees. So I mean, I won't detail all the impact that this global warming will have on all ecosystems on Earth. But this is clearly something that we don't want to see, and that we have never seen. And I mean, maybe they have some kind of humor, or they really know humans too well. They are also showing their expectations for what the emissions will be if we continue business as usual. And by extending that, also if we continue research as usual, since this is what we are speaking about here. And this is clearly something that we don't want. So it's not +2, it's not a linear increase of impact, it's +3, +4, +5, +6 degrees. And it will be, it's not only a climate crisis at this point, it's a real economic crisis, political crisis, social crisis. What this graph is also showing is that the only moments in history where humans have been able to decrease or to have CO2 emissions stagnate, it's during crisis. So you have the oil crisis here from 1972, you have the 2008 financial crisis maybe that you may remember, and you have of course the CO2, just the COVID-19 crisis that you definitely remember. So this is the only time in history that we've been able to reduce emissions. So that means that if we manage to do that, if we manage to do this or any other decrease, I mean, there will be a crisis. And there are two options. Either we try our best and we wait for the climate crisis to generate the other crisis, or we try to induce the crisis ourselves, hoping that we can control some aspects of it, and probably the last most important one would be the social one. So all that saying that whatever we do, whatever we are discussing, and these are only palliative solutions. There is no solutions. There won't be any solutions to solve this. And we start from that. And of course, we need to be a bit optimistic and keep living in this situation. So let's try what we can do in order to do the best we can, although we know that it won't be sufficient. In particular, we are here to speak about the construction industry, the act of building. This is the last graph that I'm showing. So this graph is showing the results of life cycle assessments of 1,200 recent buildings built in France, housing buildings, so single house buildings and apartment buildings built in France in the past 5 years. So those are all recent buildings. Every line, vertical line, is one of those buildings. You have the operational emissions above, so the ones related to the heating, the ventilation, the cooling of the buildings during 50 years in this case, and then you have the embodied emissions, so the one related to the construction, the production of the materials, the maintenance, and the end of life of the buildings. What we see is that there is no correlation between the two. Okay, so designers who wanted to decrease these operational emissions by improving the energy systems inside the buildings, by adding more insulations. And they did a good job with the operational emissions, but they did nothing about the embodied emissions. So is it because they didn't know, so it wasn't something they measured, probably? Or is it also because they didn't know what to do with that? Or is it because there is no solution to break this threshold that we have here? So in reaction to that, there are different ways that show, the different ways to break it, and I will focus on the reuse of components today with you in order to show how this circular activity can break this seemingly limit that we have here. Because currently there is a wasted opportunity, and this is a map not of all buildings in Switzerland, but a map of all demolitions in Switzerland that happened in the past 20 years. There are 70,000 buildings, and we can safely assume that most of those buildings were demolished, although they were of good quality. So there were still sound structures. This is a building that is now demolished to give room for a bigger building. I mean, there are economical reasons, real estate reasons that push the demolitions and the transformation of buildings. And that's independent of the quality of the slabs, the beams, and those were still good slab, good beams that could be reused. Reused, of course, is not something new. This is an example that I like to show. It's nearby. It's at the border between Germany and Switzerland. So that's a bridge that was built in 1810. 100 years later, the municipality decided to replace that bridge with a bigger one, a taller one. And so that was in the winter 1919, and in the same winter, monks from the village nearby reclaimed some of these elements. So in particular, the posts here that we see here, they reclaimed it in order to build this barn that is still standing today. The picture is from 2019, but it's still there today. And we can actually see the cuts here corresponding to the connections that were present here. So what do we have here? We have a building that is 100 years old with components that are 200 years old. And that's really the spirit of component reuse is to have products that have a longer service life than the systems they are part of. And if we are implementing, and so in an ideal world, if we are implementing this component reuse approach as much as we can, well, these would be the benefits. So per reused products, we could achieve up to 90% of greenhouse gas emissions reduction. Only certain cases, I mean, not every reuse can achieve that, but I will show you in particular what type of reuse can achieve these savings. Nationwide, and in Switzerland in particular, we can avoid 40% of waste, avoid 10 to 25% of extraction of raw materials worldwide. Of course, reusing is a new way of interacting with the built environment, with heritage. And the reason why reuse is so popular in the EU, and also for politicians now in Switzerland, is because reuse is a driver for local, non-externalizable, and renewable jobs. Because we need people to repair locally those components, to dismantle the buildings and to reuse the components in new buildings. And we need expertise at every level of every level. All right, so this is for the introduction. To clarification, because sometimes people would stop me and say, hey, you are promoting reuse, and no, I mean, in the ideal world, component reuse should be avoided. This is something to remind. So, of course, first we want to use everything that exists that is in place without changing it. If you can't do that, then we allow adaptation of the buildings, of the systems on site, and only after that we allow the reuse of parts. And only after that, I mean, then we come back here, and only after that we should allow the recycling of the material. So recycling as the last resort. And the reason why we should focus on reuse today is only because it's not common currently, or not common enough. The other clarification that I have to bring is that a lot of activities from the industry, from research as well, would focus on this aspect of circularity. So designing new components that are capable of being reused in the future. But this is only one of the two necessary aspects to do component reuse. And this is not fully circular if we are not also considering simultaneously the design of reused components. And why do I say that? It's because design for disassembly, designing for future reuse, it's not new, and there has been a lot of experiments done in the 70s already. If you remember the oil crisis that I was mentioning, it's related to that as well. So architects have been experimenting a lot of solutions to design for disassembly, hoping that by that what they are designing will be modular and in the future can be rearranged, and there's no need to produce new material again. The building will adapt. And what you are seeing now, 50 years later, is that this is not the case. There are many other reasons why, for instance, this building or the components, the pieces of this building won't be reused, despite the fact that this concrete structure is fully reversible. So it's only pieces and elements that are stacked on top of each other, so we can remove them and place them elsewhere, but yet it's not... We won't be reusing them. So reversibility is not a sufficient condition for circularity, and we should remember that. So reuse today, mainly it's for the small products in the buildings, but if we want to achieve large CO2 emissions, we need to address the load-bearing components, because this is where we have mass in the buildings, this is where we have greenhouse gas emissions as well. And it's slowly changing. Here is a an example from Belgium, where 75 tons of steel from the Netherlands will be reused in order to build the structure of this building. So it's changing little by little, probably not fast enough, and the real question is, could structural component reuse be banal again? At least that's the question that we ask ourselves at the Structural Xploration Lab. Understanding that the reason why it's not more widespread at the moment is because we don't know. I mean, there are many risks, and so we don't know. It's very easy to fear the unknown, and we are showing that those risks are not risks at all in reality. So those are perceived risks only. Just a little parenthesis, I'm based in Fribourg, EPFL, has some outpost antennas in the French-speaking Switzerland, and I'm part of the Smart Living Lab that is based in Fribourg. All right, so research now. We started with a few experiments. First, to show that it's okay as designers, since we are here to speak about design, if we don't know everything about the material. And so we started by reclaiming skis. Skis are wasted every year in big numbers, and all skis are different, and at the same time it's a composite material that it's hard to predict. We don't know how they are manufactured. Every ski is different, but it doesn't mean that we cannot build a safe structure with them. And this is what this is showing here. So combining mathematical formulations that I will not explain here, origami principles as well, showing that yes, I mean, this form finding can be optimized in order to start with straight beams of skis, even though we don't know much about them, ensure tangential contact with no torsion, and then use flat panels that are also reused on top of them. And here some further examples showing the combinations, in this case, between the elastic grid shell at the bottom and then the origami assembly that unfolds in the desired curvature once placed on the structure. Usually you would build that with timber and high quality timber laths. Of course, if you do a life cycle assessment, you will realize that this emits less greenhouse gas than the timber solution. And so the fact that there is embedded technology in the material as much as here in the skis. I mean, the ski is a very good mechanical material because it bends very well in one direction. It's very stiff in the other direction. So that's why here it made sense to use it in this elastic grid shell. But in every other material, there is this embedded technology. And that's the task of the designers, at least of architects, to understand what is this embedded technology and how to reuse it, reclaim it as much as possible. And so with students, we've been organizing for a few years now this week with bachelor students. Catherine was involved in that week at some point as well, where they had 1 week to decide where to collect materials, so what are the byproduct of the local industries that could be reclaimed in order to build a given product, a product with a given function, in this case a table, and build it, so design it and build it in 1 week. And you can only learn by doing it yourself, of course. All right. So for structural designers in particular, this change of paradigm exists as well. So conventional design, you would start from the big picture. So what is the shape of the structure that you're expecting, and then you would detail and analyze the structure up to the point where you know exactly what to manufacture. If now you start from with reused materials or materials to reuse, you start with a given inventory with members, a given numbers of members who have given cross sections and material properties and so on. And the task now is to find the best way to pick those elements and produce the shape that is needed. If I explain that with this other case study that a master student did, if we want to extend the train station roof structure of the train station in Lausanne with reused members from these these pylons in bodies. There are 3 questions that we have to address simultaneously. First is, what are the members that are worth being reused? Second is where to put them, and third is what should be the shape, the optimal shape of the structure. And this is a mathematical problem that can be optimized, and this is what we have been showing. Also simultaneously, I mean, it's not like the stock is only, is a simple stock. In reality, you have a huge variety of dimensions, even for these simple pylons, and you have to deal with that, and this is not something that you could do by hand. So the way we did it was with a ground structure approach. Here, for simplicity, it's a stock with elements of the same length, but with different cross sections. And for you can achieve the global optimum, which is, so you can say this is the best solutions you can achieve. You can also change your objectives in order to minimize the cutting, the number of cuts, to minimize the waste that you are generating, to minimize greenhouse gas emissions, and so on. And of course, you can further optimize that by changing the geometry of your truss. We have also shown that the same approach can be applied to regular structures with beams resisting in bending, where the same the stock elements would be cut in different pieces in order to better match the target structure. And we've also shown that I mean, we should be pragmatic, and we should not aim at having 100% reuse, because I mean, when you are reusing stock elements, I mean, every element will come a bit of a size. You cannot size your element to for the expected loads. I mean, the stock is constrained. You have a smaller variety, so every element will be a bit of a size. And what we've been showing here is that if really you want to minimize environmental impact, then you have to swap those oversized members with newly manufactured one. In particular, if it's a steel structure with new members that are manufactured with recycled steel. And this is true, I mean, we've shown that this is true for trusses in steel, but this is probably a principle that we can apply beyond that. So 100% reuse is never the good solution. If you're interested by that, there is a Rhino and Grasshopper plugin that you can download. This has been used by these architects to reuse actually those members from the electric pylons and build this self-standing facade that you have over here. All right, I have a few minutes left to speak about the big elephant in the room, concrete. Those numbers, I guess you show them as well. Depending on the sources, you will have different numbers for this, but it's more or less in this area, 8% of global CO2 emissions due to the production of cement alone, and concrete responsible for more or less a third of construction and demolition waste. I have to pay attention to what I say because Philippe is in the room here. So currently, what is the best end of life of concrete? It's to crush it and use these aggregates in what we will call the recycled concrete. So what is recycled in the recycled concrete? Those are the aggregates. It's good because it avoids extracting natural aggregates, to a certain extent, but at the same time, it requires as much cement as well as sand and water, and so in the end, the recycled concrete currently emits as much CO2 emissions as a regular concrete. So while this should be the very end of life, before crushing the concrete, we are showing that it's better to safely cut, cleanly cut the concrete and reuse the components with all this embedded technology that they have. Also, because these cutting operations with diamond saws that you see here are more common than what someone could expect. We've been showing that this is not a new practice. It's not something that let's imagine the future. This is something that has been done in the past. Here is an example from 1986 in the Netherlands, where this building here was, it's a prefabricated concrete building, apartment building. It was dismantled, so the panels were recovered, stored, and then used in order to build this new building. You don't see that this is a building made with reused panels, because but it's there. And there are research currently being done, again in Netherlands, for instance, showing that the approach is still relevant today for prefabricated concrete. And with all these studies, we've been showing that all the time, whenever there was a life cycle assessment that was being done, you have huge savings. So you see between 40 and 80%. And if you do a cost analysis, you realize that sometimes you lose money by reusing concrete. Sometimes you gain money. But every time the owner of the new building was also the owner of the demolished building, then there was savings. So it was beneficial for the owner. Why? Because the owner would save on the demolition cost, and because the logistics can be improved, because you can manage the planning of both operation, demolition, and construction. Also, you save on storing the pieces, you save on transport, and so on. And what we wanted to show is that what about cast-in-place concrete? In Switzerland, most of the buildings we have today, they are not prefabricated concrete buildings, they are cast-in-place. And we wanted to show that it also makes sense to extract this cast-in-place concrete and build new types of structures with this. So we built this footbridge. Catherine is here. By collaborating with this demolition company, they actually had, it only took 2 weeks to identify a source, so where to mine those components. It's a hotel near Lausanne, and that was built 10 years ago only. It was being renovated, and in the basement they had to cut those small blocks. We gave them dimensions. They provided these blocks. We further asked them to drill those holes in order to put a post-tensioning cable. You see the formwork in the back. Of course, so we used graphic statics because you have to use graphic statics. It's a post-tensioned arch, and thanks to that, you have compression always in the arch, whatever the load case. Pretty sure this is nothing new for most of you. And in the end, what do we have? We have a concrete that is as strong as new concrete. But if you do, again, a life cycle assessment and you compare this footbridge with an equivalent footbridge that is a monolithic arch with cast-in-place recycled concrete, or another one that is done with a steel arch beam, or a fourth one done in timber, you see the savings divided by 3 divided by 4 compared to these two, and then a life cycle assessment with a global warming potential that is more or less equivalent to the timber option. And if we zoom in and look at where these impacts come from, we see that a third of the impacts in our footbridge are related to transport, 70 kilometers. Between Lausanne and Fribourg, where we built it. This is something that could be reduced if you're more clever and avoid this useless transport. And a third is related to the formwork, because we were not that clever. It was brand new timber, the formwork is not reused, and so this is why you have a third. So potentially you could reduce this and then have a solution that is as green or maybe even greener than timber. Timber, people's minds seen as the most sustainable material for construction. Later on, we were invited to complete the bridge with also reused handrails and so on, and now the bridge sits in Comté, near Sion, in Vallis. What's interesting is that in order to make this happen, we had to create a collaboration between three sectors of the construction industry that are not used to work together. So the MCOOP is the cutting firm. They work in the demolition sector of the construction industry. Freyssinet came for the post-tensioning. They do regular construction, and Bridgeology helped us to assess the quality of the pieces and they mainly work in maintenance, so with working on infrastructure to extend their service life. So those are 3 sectors with different sets of skills, and in order for reuse to happen, they have to work together. We need the skills from those 3 different sectors. So this is a compression-only arch. In concrete, you have reinforcement bars, and this is where the embedded technology is. And so the next question was, we should reuse these reinforcement bars. And for that, the first project we did was with students, a student-led project. They managed to collaborate with the owner was about to demolish this building. And eventually, the entire building was cut. All pieces were cut. And together with our help, they decided to reuse these mushroom slabs. So by reusing the connections in between the column and the slabs, because this is where you have the reinforcement bars, the things that you want to reuse. And also by using the cantilevering that was there provided. So this is the demolition, deconstruction site. This is the new site, and it will be complemented with a roof structure and then straw bale walls to insulate in order to show that we can build with low-tech materials only. From a design perspective, there are interesting questions. Not only all these 3 sets of expertise had to be combined, but also there are new design tasks that emerge. The one that I'm showing here is the fact that we were not the only one who cut pieces, who wanted pieces from this building. Other colleague researchers from the HEIA, but also from Lausanne, wanted to reuse the other pieces in blue and green. And so there is a matching activity to do in order to make sure that, you can never stop a cut right there. You have a circular saw, so the circular saw goes always a bit beyond the end of the cut that you want, but you don't want the saw to go cut the other piece that you want to reuse, because this is also where you have the rebars. So how to optimize that in order to minimize the amount of extra cut that you want to avoid. So interesting questions. We went a bit further with this research here. Now we are in Basel. And the idea is that those 2 buildings are on the same site, nearby. They're about to be demolished, and this is the floor plan of the new building that will be constructed on the same site. And what the students did here, so she first analyzed the construction plans to identify the variations in the strength in the reinforcements that we have in the slab. So every color means that there is a different set of rebars inside the concrete, different dimensions, different numbers, different layout. And then simultaneously, so understanding the new spans that would be required in the new building, and then there is an optimization algorithm in order to ensure the match. So where should these slabs be cut in order for these pieces to be reassembled as a puzzle? You can flip them, you can rotate them, but you have to make sure that you can reuse them in order to build the new floor plan that was given. In this work, we started with the assumptions that every slab could be strengthened with UHPFRC, so ultra high performance fiber reinforced concrete. And these are the light gray and the dark gray shades that you have there. So depending on whether you would strengthen them below or above the slabs. And you can do that because you can flip the slabs, you put UHPFRC, the next day you can assemble the slabs. And I don't have the numbers here, but again, life cycle assessment, you compare this with a conventional construction, you divide the global warming potential by 4. So without strengthening, it makes sense as well, and this is research that is about to be published and constructed. We are showing that every slab in Switzerland built since 1956, as if the span is smaller than 3.5 meters, that slab you can reuse it today in a new building while satisfying the current SEA norms. And that's a big deal because these are most of the slabs that we have in demolished buildings today, and so those slabs, they are ready for reuse without strengthening, just like that. And here we are showing that by combining those cut slabs with, of course, reused steels. If you do a life cycle assessment, you have this impact. I don't have numbers for other slabs. It's also very slow, and this is even slower. So this is even lower, sorry. It's the end of the day, end of the week almost. So 9 kilogram of CO2 equivalent per square meter. Unless you are not building something, you cannot achieve something as low as this. Okay, last 2 slides. In reality, you will only cut what is worth being reused. So when you have the nice spans in between the beams, for instance, and still, even if you cut the things, there's still a portion of the buildings that will be crushed as usual. So what do we do with these rebels? Well, here comes a new directions of research that is still in its infancy, and the question we ask ourselves is how existing tools, the usual tools that we have on construction sites, could be hacked by extending their digital capabilities with sensing and control in order to reuse those pieces in new applications. And I think there is a video with sound showing that. So we mounted the drill on this robot. Okay, so this is the very first attempt. There are many things that can be improved in this wall. This is not yet a wall, but the principle is there. Also the principle that this can be extended outside of the lab and on real construction sites with regular machinery. All right, keep in touch for the other news on that. Thank you very much for your attention.
Thank you so much for this great lecture. I would open up for questions in the audience. Questions, comments. Sorry, I cannot walk.
Yeah. Petras already had a few questions before I start speaking. So,
just from curiosity, I would like to ask, how is the dialogue outside the academia of the people who are working in the industry? How you manage to make the dialogue and go through this whole process and make it work? Yeah. So this, I guess, is quite tricky. So.
Yeah, indeed, it's quite tricky. I mean, at the moment, we are in a phase where the goal is to show demonstrators. So to show, yes, I mean, it can happen on the construction sites. You guys have the skills, and whether you're the contractor or the structural engineers or the architects, you guys have the skills already. So this is something you can do, and something that makes sense, money, in terms of financial risks and financial operation, and that's easier because I mean those firms, they're also willing to be part of these demonstrations. Now, how to scale that up to a bigger application? I mean, what we are showing is that there are many different ways. We're only showing one way of reusing those concrete pieces, but there are many other ways. I mean, just the connections between the elements. I mean, you can ask 10 different engineers, they will come with 10 different, they come up with 10 different solutions for that. And so, yeah, little by little, but too slowly. Mm.
Thank you.
I would like to try to answer your questions. If you want to make these things happen in the real world, you need to create a supply chain. And that's exactly what we are trying to do with our project, reuse of steel sections. I can give you some additional information while drinking a beer together.
And that as well, I mean, there are so many different ways of implementing that, whether you work with a stock, whether you do on-the-fly reuse, because, I mean, the buildings, most of the buildings we are demolishing, they have the same feature. We're also showing that transport distances is not detrimental because of the savings that you have by avoiding the casting and the use of new cement. So you can transport your piece from Geneva to Senegal, and I mean, you are still saving CO2 emissions. So, and we know we can predict what type of building will be demolished, so you can also make sure that, and in the case of maybe not steel, but in the case of concrete slab, you can, I mean, you know that next month you're going to have a source available. Yeah. Yeah. Yeah, definitely, yes. I mean, those are different sectors, and they don't have the, they are not organized in the same way, and also reuse doesn't mean the same thing. So, I mean, in terms of responsibility, who takes the risk, who pushes in order for the reuse to happen. Does reuse make sense? I mean, if you are looking at steel, timber, and concrete, sometimes reuse doesn't make sense. So that's, yeah, that's the short answer.
Hi, thanks for the great presentation. I wanted to ask about how you sort of analyze these materials, maybe what role data, residual data from the previous architects or whomever, what that is, and maybe what could be done for future building projects to make sure that the maximum reusability of new building projects.
I mean, the more information you keep related to the building, the better it is. And these are the material passports and all this there. But that doesn't exist for the buildings that are demolished today. And so sometimes you can go and find the construction, the original construction plans, the blueprints. They may not be correct. So probably it was built in a different way. And so it's again the same thing as with the skis. You don't need to know everything, but you need to know, you need to assess the concrete anyway, and what's inside, the type of rebars. There are tools to do that. What's the degradation and so on. So I mean, all these techniques exist already. So we are also working, I didn't present anything about that on here, but on assessments, so how to assess the reusability of concrete for reuse. Yeah.
I would propose that the next questions we can have with a beer to end the day. And I want to end with also introducing our next talk, Dr. Rudy Gerlen, who's on the Thursday, the 2nd of November, on learning physics-based reduced order models from data using non-linear manifolds. So we're hoping to see as many of you also for this talk, and let's enjoy the apéro together. Thank you very much.
Thank you.